Hello, everyone, and welcome to today's webinar on the National Solar Radiation Database. My name's Paul Gilman. I'll just be helping with the logistics this morning. Dr. Manajit Sengupta will be presenting, and the session will consist of two parts. One is a presentation of the NSRDB followed by a Q&A session. So if you have a question as Dr. Manajit and his colleagues are presenting, please use the questions box to type your question, and then we will moderate the questions and answer them at the end of the session. This session will be recorded and posted on the NSRDB website, and you'll get an email tomorrow with that link so you can watch the recording later. With that, I will hand it over to Dr. Sengupta. Go ahead.
Thanks, Paul, and good morning, good afternoon, wherever you are. Thank you for taking the time to join us for this webinar. We are thankful for all the people who use our datasets, and our last webinar was held in 2018. So a lot of changes have occurred since then. So what I'll try to do is provide a summary of all the changes that have been done over the last couple of years. But before I dive into all of that, I just wanted to mention that the NSRDB is a big team effort with experts in various areas contributing to make this happen. I'll just quickly mention Aaron Hapte, Dr. Yuji, Grant Buster, Dr. Michael Russell, Paul Edwards, Haiku Sky, Dr. Gail McLaurin, all from NREL, and Dr. Michael Foster and Dr. Andrew Heidinger from University of Wisconsin and NOAA. They're experts in various in software engineering, in atmospheric science, and various areas which are needed to make all of this happen. And right at the end, when we have the QA, we will have our experts chime in and answer questions based on their expertise. So let's move forward. So why do we need soil resource information? Just a quick a reminder to everyone that there's various solar radiation products. The evaluation methodologies are used for the development and operation of solar energy projects on the grid. And as more and more projects come online, as the penetration grows, the requirements for the quality and the resolution of data is continuously grows. As a national lab, our goal is to provide high quality information covering as long time periods as possible and as large as regions as possible. But more importantly, our datasets try to reflect the latest improvements in the science. So that is an important component of our work as a national lab. So quickly, the NSRDB, what you see today, it was quite different, and it has evolved over the years. Pre-satellite, the NSRDB used to be a meteorological statistical model which took ground data sets, essentially meteorological data, and used a statistical model which used there was information from human observers saying about cloud cover, and all of it was translated into solar radiation. That happened for the first version where you have the TMY3, and then it was for 239 stations. It was updated to 1,454 stations. At that point, since 1998, the satellite became available. So as you see here, the NSRDB MTS2, that included partially satellite data and partially these ground data sets. But then the current version of the NSRDB is all satellites. The data starts in 98 and goes to 2019 currently. Of course, as most of you know, the satellite got upgraded, and from 2018, we started getting data at 5 minutes and 2 kilometers. So as time moves forward, we're getting much higher quality data, and our time resolution improve. Also, time and spatial resolution increases. We also have more channels in this current satellite, so expectation is that the accuracy of the product also improves. So the outline of this talk, excuse me, the outline of the talk today is I'll talk about the underlying model, the physical solar model, what's new, what's happening in the NSRDB, what's gone on for the last 2 years. How do we ensure quality of the data and validation of the NSRDB? How do we disseminate our data? We talk a little bit about our website, our recent publications, and what's expected in the near future, what's in the pipeline, what our planned future work is. So let's start with the underlying physical solar model, which forms the model behind the data. So the physical solar model, essentially, as I just mentioned, most of our all of our information is mostly satellite based. So what we have here in this slide here is you have the GO satellite, and which is essentially used to derive cloud properties. By cloud properties, what I mean is the cloud mask, the cloud optical thickness, what type of cloud it is it ice cloud or water cloud, because that matters when computing radiation. Then of course we have MERA-2, which is a reanalysis data set from NASA, which is essentially assimilates a lot of different satellite and ground-based observations, and creates and delivers hourly data sets of the atmospheric profile. There's aerosols. So the MERA-2 is heavily used for the ancillary data, which is available in the NSRDB. There's of course the MODIS satellite, which is a polar orbiting satellite, which also contributes to the aerosols. And then the surface albedo, which is an important part of radiation calculations, is also derived from MODIS. And we also have a snow cover from the integrated snow data sets available from NOAA. And all of these properties ultimately are used in the FARMS model. The FARMS model was developed by NREL. It's a fast radiative transfer model, which gives us direct computation of the GHI, the global irradiance, the diffuse irradiance, and the direct irradiance. So it's a general scheme of things for the NSRDB. So quickly say what's unique about the FARMS model, because the FARMS model is an integral piece of the NSRDB. What happens is normally if you use a radiative transfer model used in meteorology, it's extremely slow and it's not tractable to do millions of computations. So what the FARMS model does is has parametrized the cloud transmittance as a function of optical thickness and solar zenith angle, and which essentially allows us to do extremely fast computations. The accuracy, and I have presented this at various conferences and meetings, and there are papers on this, but what happens is this model's accuracy, the accuracy of this model is equivalent to the slower meteorological models. So we verified that. So what's now moving forward? What's new in the NSRDB? So let's quickly look at what is available when you go to our NSRDB website and try to get data. You can see here the circles in red. These have been available. These circles, these have been available since our last webinar. But the green circles are you can see here are new data sets. You can see there's quite a few of them. And I'm going to go into a little bit more detail about what's new. But as you can see here, you see the PSM version 3, which is the workhorse, which is the original half-hour, 4-kilometer data. And of course, although it's in red, it's every year we update this data and you get a new year of data. The same thing happens with the TMY. And just quickly mention that we update the TMY as we add a year of data, so you get a new TMY. And we currently make 3 years of TMY, three versions of TMY available, and we kind of deprecate the previous version. So that's what our plan is, to at least we'll keep 2 to 3 versions of TMY available for our users. So now going into a little bit more detail about what's new. So we of course have our 30-minute 4-kilometer data, but as you can see, as I mentioned, we have an upgraded satellite which provides us 5-minute data at 2 kilometer nominally. So what we decided was, of course, we'll keep providing the 30-minute to maintain continuity, and the 30-minute is an average of the 5-minute data, but we are also providing the 5-minute data at 2-kilometer resolution. The 5-minute data is, of course, for the continental United States, and while the data for the rest of our domain is available at either 10 or 15 minutes, depending on which year. So we started 2018 is 15 minutes, and from 2019 it's gone down to 10 minutes. As you can see here, there's some advantage of higher resolution data, and I'll take a minute to explain this graph. Here's an example. So if you look at it, the observations, which is ground measurements, it's in blue here. It's a 5-minute average of the observations, and the NSRDB at 5 minutes is in green. On the other hand, the red line is the average at 30-minute average for the NSRDB, and the orange here, ochre color, is hourly. As it's obvious that the 5-minute data has a big advantage. It can represent the variability we actually see in ground observations. So technically, I would say that there is definitely value in using 5 minutes if your process or if your requires representing this variability. So I would advise you or users to have a closer look at this. The next one is, of course, is we have a spectral data set available from the NSRDB. The spectral data is essentially available on an hourly basis. You can get 1 year of data at 2,000 wavelengths, and you could choose your plane of array. It's essentially, as if you're aware, that making spectral calculations is computationally expensive. So our team, and a shout out to Dr. Yuji, who developed the FARMS for narrowband irradiance and tilted surfaces, and this process can run in 2 minutes on one processor and provide you a 1 year of spectral data. We developed this mainly for users who are exploring different technologies, and ultimately with the hope that this can provide more accurate downstream modeling for various photovoltaic applications. The next thing we made available, and this is essentially to address questions about reliability and degradation of PV panels. UV seems to be an important factor. So This is a model which is surprisingly accurate given the simplicity of the model. All we did was we computed. What we found is that the ratio of global ultraviolet to GHI, which is represented here as REV, is a reasonably stable number with weak air mass dependence. That's what we found. So we essentially chose 15 locations and used SMARTS, which is a clear sky spectral model to calculate GUV and GHI for various possible atmospheric conditions, various solar angles. So then ultimately what we did was we fitted the REV for each location to a fourth order air mass polynomial. There's slight difference in its coefficients, and you can see it on the right hand side. These dotted lines is the range of basically the range you get for the REV and for different air masses. And ultimately what we did was to simplify it even further to derive these solid black lines. As you can see here, the green and there's the solid black and the solid green. The solid green is, of course, two different flavors of UV are available. One is for the 295, 385 nanometer range. The other is the 280, 400 nanometer range. And on top, you can see here is we validated it. There's a few papers we've written on this, but here's an example of validation. As you can see here, that this red line is essentially this black line is a 1-to-1 fit, and as you can see, the model UV is on the vertical, the measured UV is on the horizontal, and it's pretty accurate as in this example with the NBE of 6.8%. So they're extremely useful for applications which require the total UV for annual amounts of UV for looking at life cycle predictions. The next slide, it just shows essentially that we moved to a more transparent versioning and this is available on our website. Just wanted to mention that we started, of course, with model version, PSM version 1, 2, and we're at version 3 now. And the most important thing I wanted to point out was when we started with version 3, this was when we got, when MERA 2 came online. The MERA 2 is, as a reminder, is the reanalysis model output from NASA. It provided us hourly aerosol data, and that is when we shifted to model 3.0. Of course, there were other changes, minor changes, which did not require change to version 4.0, but essentially, as another highlight is we refactored our NSRDB processing code in 2018 to make it operational for our high resolution time and space data. We did need to change our code, so this represented a version change. But essentially what I wanted to mention here is that as our science improves, we will have version changes with an attempt to reprocess all our data, not just moving forward, but of course there are some limitations, but we'll try to always update all the data set from starting back from 98. Every time we try to make a major change in our modeling effort. So another product we made available, this is, we developed a very simple model to downscale our data sets. And here's an example. We put this data online, and this is only for Puerto Rico. This is part of a project, but this model essentially downscales our 4 kilometer 30 minutes to 2 kilometer 5 minutes. So this model performs pretty well, and we put this data online. And future work, and I'll discuss this, is the possibilities of making this model available more ubiquitously. Then finally, we also have, we leverage our NSRDB. We try to, like I said, we try to provide coverage, and there was funding from the international programs at DOE requesting us to generate data. So we, for the meter sets Indian Ocean, and we recently made this data available for 3 years from 2017 to 2019 using our PSM model, the physical solar model. For those who are interested in this region, please check it out. Moving to data quality and validation, I'll just quickly go through what we do here in terms of ensuring that our data is of good enough quality. We check every variable to see whether we're exceeding a set physical limit or variables are checked. Then there's a processing quality flag which is available to all our users. I just wanted to point this out. So there might be, of course, as you know, when you measure and take measurements, there might be missing data sets, missing points. So what happens here is that it indicates that there's flags which indicate there were missing cloud properties, or because of the model's uncertainties, there's unphysical irradiance which have been either filled or corrected. So it's just very useful information for our users, which I would suggest you look at a little more closely when you're doing your modeling efforts. Then we, of course, do a qualitative map review. Of course, we can't look at every timestamp. We look at a few timestamps just to see visually whether the different variables represent, the maps are representative of what we expect them to be. Of course, this is very useful occasionally, and has led to us identifying issues with our processing. And finally, we have the ground truth validation, and I'll just we've talked about this validation of the NSRDB data in various forums in way more detail with published papers, but I'll just still do a quick summary. It is very important for our data quality is our users, because public data set, we have a lot of users, and sure enough, our users use the data at in various locations and regions, and they occasionally do point out very specific issues. Extremely helpful for us, both for our scientific research and also making our data set better. Really, thank you to all our users for doing that. So quickly now on the validation side, we do validate our data, our NSRDB data against ground measurements, and this is just an image from our publication. As you can see, we use high quality ground data from NOAA. The SERFRAT stations are here represented here, and as you can see, it's all around the country. On the left-hand side, because our algorithm allows us to identify clear and cloudy skies, so we can parse our data. So I'll just quickly explain what's here on the left. There are 1, 2, 3, 4, 5, 6, and 7 panels here. The 7 for the 7 stations, and on each of these horizontal, these are all kind of contour plots. The blue is for all the data, the all sky from 98 to 2019. The clear sky is represented in yellow. The cloudy sky is in green. There's missing data, of course, there's more uncertainty, as you can see here. But one important thing to note is that, of course, the percentage of data here is way lower than in this. So these contour plots show that the NSRDB produces reasonable, good quality output when compared to ground measurements. Here's another way of representing our validation. As you can see, on the top panel is the MBE, and the bottom is RMSE. mean bias error and the root mean square error. Again, there's GHI in the left panels here and DNI in the right-hand panels here. You, of course, have, again, the same color scheme with all sky, cloudy sky, and clear sky. As you can see, the MB, the biases are within plus and minus 5% for the GHI. And this, if you want more details, please refer to our other publications or send us an email and we'll send you those publications. For data dissemination, I will ask Paul Edwards to talk about this. So Paul, can you please go ahead?
Yes, thank you very much, Dr. Sengupta. Hello, my name is Paul Edwards. I am a software architect at NREL. My responsibility is developing all of the code behind the data distribution services, as well as the NSRDB data viewer. Almost all of the services. I didn't develop the HSDS. And so we have created tools to provide access to the data through a variety of different means. Our goal was to enable users with different use cases and different purposes, methods for downloading the data to have access. So there's a user interface available at the maps.nrel.gov/nsrdb-viewer address, which allows for downloading the data through a user interface that is accessible to just about anyone. We also offer some programmatic methods for downloading the data, which I'll talk about in more detail, but essentially there are a couple of different HTTP-based APIs that people can use. One of them is based on a service developed by the HDF5 group called HSDS, and the other one is more of a traditional API that we at NREL have written. And so the final method that we're highlighting here is that the NSRDB is also offered as a input data source in the system advisor model developed at NREL, which you can use fairly seamlessly if you're using SAM. NSRDB is available without much extra effort there. Next slide, please. So I'd like to discuss the different data access methods going from the finest grained up to the coarsest grained. And so the difference in each in many ways comes down to how much data you need and how much control you want over the specifics of the data you receive. So the finest grain access we have made available is via AWS, Amazon Web Services, and you can download the full data set via AWS if you wish. It is close to 100 terabytes in size, and so downloading the entire data set is not a recommended solution, but it's available if that's desirable. We also are offering the HDF highly scalable digital service, which is a fairly low-level wrapper around the raw data itself. And the power of HSDS is that you can request any of the data and you can slice it and dice it in any way you wish. And so you're not limited to downloading data for a given year at a time. You're not limited to downloading data across contiguous points at any given time. And so it offers a greater amount of data per request as well. And so users who are power users who are really looking to download large portions of specific data, typically those are the types of users I would anticipate taking advantage of the HSDS service. Of note, the raw data requires some post-processing. There are scale factors and offsets that need to be applied, and so when you're accessing the raw data through HSDS, it's important to recognize that there are a couple of steps to using the data. Next slide, please. So stepping up a level from the AWS sort of direct access services, there are a set of APIs that we host at NREL, and the slide is showing some of the documentation for one of the endpoints. The slide is not in and of itself useful, but it's simply a reference to point out that if you're looking at accessing the data via the API, your best resource is going to be to go and look at the documentation. The documentation lists each parameter that the API accepts, as well as showing every available option for each of those parameters. So the API is useful because it produces CSV files as its download product, and those CSV files are already post-processed. They have the data has applied the scale factors, the offset has been applied, and they're put into an easy to digest format. So I think where I see the API's sweet spot is for users who want a lot of data, but not massive amounts of data, and who are looking for an easy way to, say you want to write a script that can loop over a set of points and download data for those points. Limitations of this API, it only provides data in 1 year at a time chunk. So you have to request it for a specific year, say 2018, and you will get 1 year of data with each request. Also, I'd say one of my most, I receive multiple requests every week of users asking if they can have more of the data. So we have rate limits that we have assigned to these APIs, and the rate limits are sometimes restrictive to users. Those rate limits are based on the amount of available hardware we have, and so there's it's a fairly stringent system, and we are handling tens of thousands requests per day, generating dynamic archives out of hundreds of terabytes of data, and so it's quite difficult for us to offer custom rate limits. However, there is on this documentation site a guide that I wrote which offers some helpful tips for users who are looking to get the most out of the API. I think one of the most powerful aspects of this API that is also one of the least used aspects is that you can download multiple locations, multiple years within a single request. And those single requests can be quite large. And so, researching these documents and crafting your requests to get the single most data out of a single request is probably like I said, it's sort of a powerful feature that I don't think a lot of people take advantage of. Next slide, please.
No, did I skip? Okay, go ahead.
That's right. Yep. And so stepping up one more level for a more casual user or someone who isn't looking to download many data files, the data viewer is a great resource. In addition to simply accessing the raw data, the data viewer also has a lot of visual data. So this provides a great way of researching the NSRDB, of seeing how the data set changes over time, and it's quite intuitive to navigate and very graspable, very obtainable. And so there is something specific here that I wanted to point out, which is that there is a call out in the bottom that says download layers. And we have seen some confusion in this feature. Those downloads are specific to the map layers, and so they represent a single variable for a single year in one of the data sets. And so if you download that, you're not getting the raw data, you're simply getting the data that we use to create this map layer. So those downloads would be useful if you were interested in a map. So say you're putting together a presentation or you're writing a report, and you'd like to get the shape file to use to generate a map and style it the way you want to present this, that is what those downloads are useful for, but they are not the raw data, and so they should not be confused with the download tools. However, in that layer tree, you can see we have presented the PSM data and other data sets in a variety of different ways across a variety of different years. You can view multiples at the same time or one at a time. You can see the metadata about the data, and you can download the map layer if you'd like to use that data for presentations. Next slide, please. This is the download feature that I was referring to. And so if you're interested in using the viewer to access the raw data, this is the tool you would want to use. So in the upper left, you would select the download data tab. And then you have the option of either downloading for a single point, or you can draw a box. If you draw a box, it will provide you with download of all of the data points that are within the extent of the box drawn. Next slide, please. I just described that. Next slide, please. And so when you've made your choice, you then have the option to, you're working right on the map. So you either click a point or you draw a box right over the map itself. Next slide. So the first step for downloading the data is to enter a few pieces of information in this form. I think it's really important to note that we don't use this information for any purpose other than internal only, unless you click the keep me informed. If you click the please keep me informed checkbox, then we will only use your email address to send you updates about the NSRDB. So that data is never shared outside the lab, and even within the lab, the data is never shared. However, we use it to calculate some statistics, which we basically use to convince DOE to continue to fund this project for us. Also, the email address is necessary because the way this tool works is it generates a zip file and then it sends you an email with a link to the download. The reason that's important is because when you are if you're requesting a large amount of data in a single request, it may take a few hours for the data archive to be generated. We're generating them on the fly from data on the servers, and if we have a large amount of requests coming in concurrently, then some of those can be queued in a job queue, and they might not even start processing for a few minutes, and then it can take them up to 60 to 90 minutes to complete processing, depending on the nature of the request. So the email address is important. It's important that it be a valid email address because that's how you'll access your data when it's produced. Next slide, please. Right, so this is the download tool. I think it's fairly self-explanatory, so I won't spend too long, but here you have the selection of the years you wish, the attributes you wish, any specific options. I did want to make mention that this user interface is built on top of the API that we saw previously. So everything that's possible in the API is conducted via this user interface. However, the API offers a lot more fine-grained control over your requests than is accessible here through the viewer. So you can get closer to what you want by using the API directly than you can here from the viewer. But I'd say 85% of what you can do in the API is here in the viewer. And so there's also a handy little download limit indicator on the bottom. I touched briefly on the fact that all of our services are rate limited to ensure that no small set of requests ends up completely taking up all of our server capacity and affecting all of our users. And so here in the viewer, you can see a little progress bar that essentially is indicating how close you are to the maximum limit for a single request. Next slide, please. Wanted to highlight that even the on-demand tool, so these are data sets that are not only are the download archives generated dynamically, but the data itself is being generated dynamically. And so you can enter, next slide, please. So if you've chosen a fixed tilt system, you can enter the parameters defining the nature of your fixed tilt system, the tilt angle and the azimuth. And when you submit this request, it is generating this data from the raw PSM3 data. It takes that and generates the spectral data. And this process takes a little longer than the process to simply create a CSV file and download that. So if you're submitting these requests, you should expect a little bit of extra latency while it dynamically generates that spectral data from source. Next slide, please. A one-axis tracking system does not require the input of the tilt and azimuth angle. Next slide, please. So I touched on this already, but when you have completed all of your inputs and you hit the download data button in the lower right of this tool, you receive this pop-up, and it basically explains that your data is being generated. When the server, your job has completed the job queue, you'll get an email, and the email will have a link the link will be to a zip file which contains, the CSV or multiple CSV files that you requested. Next slide, please. And here's what the email looks like. It is valid for 24 hours. We don't store every download request infinitely. We assume that people are going to download them once, and that will be that. Next slide, please.
Yes.
Okay, so I think that concludes the data dissemination part. Dr. Sengupta.
Thanks, Paul, for your clear presentation. I'm sure it's extremely informative for all our users. So now moving on to our website, and we made significant improvements to our website. We do request our users to visit our website because there's a wealth of information there. It provides the current links to the current and archived datasets, the methods used to generate the datasets, various download instructions, as you can see here, and then, of course, the latest publications. So we do provide our latest publications, a link there. The content on this website is, of course, regularly updated. The Contact Us form allows our users to ask questions or gain additional information directly from the NSRDB team. So please take a moment and if you see anything you're missing, it would be good to have feedback from you as our user. Another important thing on this website is we provide this announcement as of September. As you can see here, here's a latest update and revisions. We have this banner here. So this is a please check this occasionally to see if there is any announcement, and send us an email if it impacts you in any way. Another important part of our website is that there's archive page for the old NSRDB data. Remember, I mentioned we had the older versions of the NSRDB, and for those who were using the Red Sea website, this website was decommissioned, and all this data now resides on the NSRDB website. Of course, we request and we recommend to users to use the newer NSRDB data. As I explained, the older data was generated using a statistical model with no real measurements. Here we have the satellite, which is real observations. So from our scientific opinion, the quality and the accuracy of the current data is much higher, than the TMI data sets are much more representative than the older TMI data sets. But nevertheless, if you really are looking for this old data, it is available for download from the NSRDB website. So future plans. One important thing what we found is that in cloudy sky situations, while the GHI can be computed extremely accurately, the DNI sometimes is not as accurate, has biases occasionally. The reason being that if you really think of DNI in a model versus a measurement space, a measurement in using a parheliometer has a 5-degree field of view. While when we do a numerical modeling from a rate transfer model, it generally uses a Lambert law, and it is basically an infinite narrow beam and doesn't consider the angular extent of the solar disk. Of course, when you have thin clouds, it's the solar disk, the impact of the scattered radiation around the solar disk is still significant, and that's what you see when you measure it. So there definitely, when you compare the two, there are differences. So another way of modeling is the empirical modeling between GHI and DNI, which again, this depends on data availability at location and time. So that leads to uncertainties. And then there's a physical model, which is time consuming. So what we did was, and this is an improvement, what we've been doing generally, and as you can see here, 2 examples of what I just mentioned. Horizontal axis is DNI from measurement, and from on the vertical axis, you can see it represents DNI. On the left panel, the DNI from the Lambert model. As you can see, because it's an infinitely pinpoint representation of DNI, we underestimate it. On the other hand, if we use some sort of an empirical modeling, we overestimate the DNI. So, and this is, remember, we're talking about cloudy sky situation. So we've developed a new model, and Dr. Yuji has led this effort, which we're going to implement in our newer version of FARMS, and this will essentially solve this problem. Essentially, what we're going to do is the transmittance can be given by the integration of radiance over different differential solid angles, and that's what we are looking to do. I won't delve into the details of this slide, but essentially, if you look closely, what we're doing is we have this lookup table of cloud transmittances, and there's a Lambert law and there's a FARMS model. All of it combined will give you a cloud transmittance, which will give you your DNI more accurately in cloudy sky situations. So other feature development work, this year we're working on adding a feature where if you, which is basically providing terrain-aware irradiance, essentially terrain effects will be taken into consideration, and our plan is ultimately to provide a feature where you could download the data as is, or if you want to activate terrain awareness, then the data will take essentially account for that. Another thing we published on and we're still working on is TMY. One thing we found, and just wanted to make our users aware, that if you use the regular TMY, which is essentially a median for all the data, and it's computed in a horizontal, and you use it for a tilt, which we normally do when we're doing rooftop or any other PV application, that is no longer a TMY for that particular plane of array. There are biases, and this is because it's not always uniformly cloudy or clear during the morning, during the whole day. Some regions might have preferences that it gets cloudier in the afternoon, and these type of weather phenomena essentially creates biases in your TMY. And so what we need to do ultimately is to be able to create TMY by running the time series to generate the full plane of array and create the TMY on that plane of array data. One of our plans is to develop an on-demand TMY in the plane of array. And this is an effort, sorry about that. This is something we will be coming down the pipeline at some point. Another thing is our new satellite has high resolution cloud properties. So at 500 meters, of course, providing data at 500 meters to a user, it's the volume of data is blows up. So, but there are other ways to use this, including using a cloud fraction to be able to get the proportional clear and cloudy regions within the 2 kilometers and use that to improve the accuracy of our current data sets. Of course, another effort which is ongoing is we have cloud properties. Right now we are filling from times before and after, but our goal now, we have this project which is ongoing to see if we can get, because occasionally the cloud properties are not derived because of high zenith angles or various limitations, but we do have the raw satellite measurements. So we're seeing if we can derive the cloud properties directly using machine learning based methods, and this will be implemented in the future. Another effort we are ongoing is, and we might, this is in the future, of course, depending on funding, is to add a precipitation product, because this is something of which the soiling community is interested in. And of course, for snow albedo determination, we want to improve the product, and we want to determine whether there's new snow versus old snow because albedo changes. So we want to incorporate precipitation data into that determination. And of course, the other thing I talked about was downscaling of NSRDB data for Puerto Rico using our model. We want to provide a service where we can provide on-demand downscaling of the NSRDB data to your users. So finally, our recent publications, just a request to all our users, if you're using our data and you want to refer to our data sets, please use this reference. This is available on our website, and the publications, the paper is also available freely. You don't have to be subscribing to the journal. We have made this publication freely available to all our users. So, and it contains all the primary information about the NSRDB. So please download this paper and refer to it as much as possible. We've recently published a paper. This just came out. It's hot off the press. This is an analysis of the spatial and temporal variability of the NSRDB data. We took the 1998 to 2017 data set, and this has just been recently published. So if you're looking to see how the solar radiation varies in different regions, please have a look at this. And another thing which some of you may be aware of is our Solar Resource Handbook. This is work which is done by over 40 leading experts in the world. It is under the auspices of the IEA. We have an IEA task, PVPS Task 16, which produces this handbook. This handbook is currently being updated, and the latest version should be available by around the end of this year. There's a wealth of information from the world leading experts in various areas of solar radiation forecasting, modeling, measurement. So this is probably your go-to resource, which will be freely available from the NREL website. So that's it, and thank you all for attending, and we will now take questions. So Aaron,
yep.
Please go ahead.
Okay, so thank you, Manojit. We'll answer as many questions as we can, and I will assign a question to Manojit or one of the panelists, and we'll answer them accordingly. We might not answer all of them, so, but we'll post all the questions and answers in our website in a couple of days from today. So to go straight to the question, so this is for Manojit. Is the 5 minutes data temporal resolution represents an interpolated value? So to answer this, maybe Manojit, because there are many questions regarding this, if you could go to slide number 9 and maybe elaborate a little bit about the Puerto Rico 5 minutes versus the PSN V3 5 minutes, and also some explanation about the IODC data too.
Okay. Let me see, where is my Puerto Rico 9? You asked me to go, okay, slide 9. So 5 minute data. For the Puerto Rico, this is essentially what it is taking the 30-minute data and interpolating it to 5 minute using a model. Where this model, just a little explanation of what this model does. Very simply, if it's clear to clear, of course, we assume the intermediate period is clear. If it's cloudy to cloudy, we assume the intermediate period is cloudy. But of course, we interpolate the cloud properties, the cloud thickness, optical thickness, and then do the radiative transfer. So all of this work is done on the cloud space as opposed to the radiation space. And so the cloud, if it becomes thicker or thinner, is represented ultimately in the radiation. If it goes from cloudy to clear or clear to cloudy, then what we assume is that it happens at the midpoint of the time period. So when it's 30 minutes, it's 15 minutes of clear and 15 minutes of cloudy. So if it goes from cloudy to clear, then it happens in 15 minutes, and our optical property, the optical depth of the cloud, goes from whatever its value is to 0 at the 15th minute. The reverse happens when we go from clear to cloudy. So that's the model, and it's only available in this Puerto Rico data set here. The actual 5-minute data from the satellite is available since 2018. And this is because this is our new satellite, and this data, so we have made this available. This is no interpolation, this is actual observation using the satellite. So you do have data available from 2018 at 5-minute resolution. But of course, we haven't provided 5-minute data going backwards in time using our model for all locations. It's only available, like I mentioned, for Puerto Rico. So Aaron, does that answer the question? Oh, and the IODC.
Yeah.
The IODC is essentially, it's the Indian Ocean data coverage region. Essentially, it is a different satellite. It's so the Europeans run 2 satellites. There is, of course, the actual Meteosat, which is essentially geared towards covering Africa and Europe, and it sits in the Atlantic Ocean. And then there is this other satellite which sits in the Indian Ocean and which covers a little bit further east. This data set is a continuation. Our effort was, we used to have the SUNY India, as you can see this was used, this is data from 2000 to 2014 using the SUNY model, 10-kilometer hourly. So what happened was that we were asked by DOE International as part of collaboration with India to update this data set. The Meteosat 8 is similar, has similar channels to our newer GHOST satellites. So we were able to derive cloud properties, but that satellite is only available since 2017. So we produced 3 years of data, and this data is available at 4-kilometer resolution. I think it's every 15 minutes, and it's downloadable. So that's what this MSG IODC PSM version 3 is. Aaron?
Okay, thank you, Manju. And the second question is regarding the downscaling tool for the Puerto Rico. And also maybe you can explain it in the 5 minutes too. Can it capture the variability accurately? And for the Puerto Rico, can you, so you already went to 5 minutes, is it possible to go all the way to 1 second to interpolate?
So the model will run at whatever timestamp. The main issue is we need to think of it in the physical sense. Okay, so let me see. Let me first talk about the variability. So when it's clear to clear or cloudy to cloudy, when it's clear to clear, of course, there is not much variability. We just have clear sky calculations. When it's cloudy to cloudy or the other ones like clear to cloudy or cloudy to clear, of course, our cloud properties go down. So there is that variability. The cloud changes. But superimposed on top of that is a natural variability within the cloud property. So even though we go, say, let's assume an optical depth of 1 to optical depth of 0 in 15 minutes, let's assume when we're going from cloudy to clear. But superimposed on it is a 5% variability. This is essentially represents some of the natural variability. But going down to 1 second, I don't think it is. So one thing to remember, though, is that we have 1 second, and that is temporal. Then the other thing is spatial. So if we are considering a point measurement and we take 1 second data, that's quite different from a 1 second data covering a 2-kilometer area. So even if we were to do an experiment in say, let's assume we have data in Hawaii for 1 year, which measures at 1 second. If we start looking at the average of the data at 1 second, you can see it's all smoothed out. So technically, while we could, but again, there is a little bit of variability, but 1 second it's way more smoothed out because of geographical effects. So we should, but I would say that no, our model is not there to represent a ground measurement. So this model is not geared towards representing pinpoint measurement of the ground, measuring at 1 second, and that variability.
Okay. So the next question is, how often is the data updated? And also, some of the users, they need recent data sets. So can you explain that?
Yes, so our data set is updated annually, and that is what DOE requires or wants us to do. If an overwhelming number of users think that this is something which they really need, or of course there are commercial data sets which are available at much higher frequency. But if there's something overwhelming need, this is something which needs to be communicated to DOE, because this sort of decision is a DOE decision. Of course, we have the ability to generate this data, but again, DOE decides how frequently we provide updates of this publicly available data set.
Okay. So the next question is to Paul Gilman or Haiku. Will the presentation will be available soon?
Yeah, sure, I can take that. This is Paul Gilman. We'll be posting the recording of the webinar along with a copy of the presentation slides and a transcript of the Q&A session on the NSRDB website.
Thank you, Paul. So the next question.
Yes, and this is Haiku, just to add on to Paul's comments.
Okay. Go ahead, Haiku.
Sorry, Aaron. I just want to add on that the announcements page for the users is where they can find all of the content from this webinar on the NSRDB page. Sorry, back to you.
Okay, thank you, Haiku. The next question is to Manojit. Can the satellite information be relevant for soiling modeling, that the NSRDB has a plan to include soiling information?
So remember, we talked about precipitation, and we talked about aerosols. So essentially, the soiling is a combination of the aerosols and when precipitation happens. So it's a derivative data set, and it definitely can be done. Essentially based on those two pieces of information. Again, this is, if it's a product which is useful to our users, our suggestion is that if you can provide, most of our products, we request that our users provide us, like, this is an important piece of information, can you do this? And when our model is to approach DOE and request funds to create something like that, and then we work with other experts, the soiling experts. There are a lot of soiling experts at NREL and other national labs. We pull all their expertise, and and we can definitely develop a soiling product through the NSRDB. It's by pulling the experts, it's more of like, if we think there are sufficient users, and this would depend on active feedback from a user. So again, while we do not send you guys emails on a regular basis soliciting information, if there is really, if you think there is pressing need, it depends on if we have around 150,000 users overall during the year. So if our users overwhelmingly request for something and we can do it, we can approach DOE and try to make it happen.
Okay. Thank you, Manojit. So the next one is, this is for Manojit too. Is the 30 minutes data averaged, and does it represent the end of the hour, middle of the hour, or beginning of the hour?
The 30-minute data is not averaged for up to 2017. It is 30 minutes is instantaneous. for, and Aaron, correct me if I'm wrong, from since 2018, it is averaged, but what it represents is 15 minutes before to 15 minutes after the timestamp. That's what is being represented from 2018 onwards.
Okay. Yeah, I think that's correct. And so the next question is, what is the elevation of wind speed measured and reported by NSRDB? I can answer this one. It represents 2 meter from the surface, and we get that data from MERA-2. And related question, maybe Manojit, can you elaborate on how the MERA-2 data set and MODIS aerosols are downscaled to the NSRDB location? And with that also maybe explain also how the aerosol data set represents the wildfire smokes that we see right now in the US.
Okay, so the aerosols, of course, what happens is the process, we use MERA-2. MERA-2 is, of course, a coarser resolution data set, but one good thing about MERA-2 is it assimilates most of the satellite information. So MERA-2 should contain information about the elevated aerosol levels from the current wildfires. It should show up, but we will definitely have a closer look at when we create our new data sets. So it should be represented. The other thing is we are talking about Aaron downscaling, I guess. Yeah, and the downscaling uses there is a model where, of course, what we see is that if MERA-2 is around 50 kilometers resolution, and we consider that it's representative of an average elevation for that pixel. And when we start to go to 4 kilometers or 2 kilometers, what we do have we have a scale height which is around 2,500 meters. So essentially, the assumption is that there's an exponential scale height, and as our elevation goes, we first push all our aerosols to the sea level at 0 degree, at 0 meters, and then for each pixel we scale using this exponential scale height. The aerosol, of course, goes down, and the air becomes cleaner as you go to higher elevation. So that's the model we use to essentially. This is a Chris-Guimard model, and this is what we use to downscale our aerosols to the higher resolution. Did I answer all those questions, Aaron? Or
yeah, you got it. This is question to Paul Edward or Michael Russo. Do you have an example Python script on GitHub to download multiple weather files on multiple locations for multiple years via API? Paul or Michael?
So I post an answer in the questions section. We have many examples of using our HSDS API and server to access the data. You can go to github.com/nrel/hsds-examples. You can also find examples using our resource extraction tool, Rex. It's at github.com/nrel/rex, REX. Both of those will provide examples on how to use HSDS and how to access slice data however you want, as Paul explained during the presentation.
Thank you, Mike. And the next question is to Manojit. What is the difference between PSN and Solar Anywhere or Solar Anywhere datasets or any other datasets?
Okay, yeah, so if you're aware of Solar Anywhere uses the SUNY Richard Press State University of New York model. Essentially, what that model is a representation of cloud indexes. What it is, if you look at it, is a ratio of essentially what the clear sky is to to what your actual radiation is. This is essentially a statistical model. In a way, it's a regression which matches what the satellite sees from the top of the atmosphere and what you measure on the ground. So what gets reflected back to the top of the atmosphere and is caught by the satellite is related to what you would measure on the ground. That's kind of the theory behind the semi-empirical model. Of course, there are a lot of additional features in there, a lot of additional methodologies being applied and nuances. I was just trying to simplify the overall method. On the other hand, the physical solar model is slightly different because what it does is it is a two-step process. First, what it does is it takes all the satellite channels, all the 16 channels for the current satellite, and tries to do a few things. First, it identifies whether it's clear or cloudy. So when you have clear or cloudy, it's a cloud mask. And so we identify that first. And then when it's cloudy, we do a few things. We get to the cloud properties, which is how high the cloud is, whether it's an ice cloud, because it has different scattering properties, or whether it's a water cloud. And then, of course, what is the size of the particles of the cloud and what is the optical thickness or how thick the cloud is. So all of this information then feeds into the second step, which is the radiative transfer model, and which directly calculates GHI, DNI, and diffuse. It's a direct calculation, and it's done for the clear sky. Of course, we get the aerosols and we do this calculation, and it uses RES2, which is Dr. Christian Gemart's model. For the cloudy sky, we use the FARMS part, and we do this calculation. And for Solar Anywhere or any of those semi-empirical models, what it is capable of is generating a GHI, and then then there is another model which you have to use, the decomposition model, which then separates out and into DNI and GHI, and that's based on ratios of diffuse to global. And there are various models, but one of them is, of course, has been developed by Dr. Richard Perez. So that's what most of the commercial available models are. That and SolarGIS are use similar type of methodologies.
Okay. Thank you, Anju. The next question is to Paul Edward. Is it possible to get ahead of time if there's going to be any change on the API, or if there's going to be any downtime on the NSRDB viewer or API? Could you explain?
Yeah, so this is an area in which we're seeking to improve. So we've recently implemented a notifications page on the website, which Haiku referenced a moment ago. And so we're intending to post, known downtimes for maintenance and such will be notified. Also, the API has a feature where, while it doesn't notify us ahead of time, it does respond if the data download API is out of service for any reason. The API will respond with a response that indicates as much. So it lets you know that this is not an error, something didn't go wrong, but we're actually down for maintenance. And so I will sort of caveat and say we do occasionally have outages, whether it's related to networking here at the lab or related to just an increase in load causing slowdowns. And so we don't always have advance notice ourselves of when things are going to crash, which I guess is sort of stating the obvious, but it does happen. Yeah, that's what I'd say.
Thank you, Paul. The next question is, I think, to all of us, can you post a reference where we can find the definition of cloud types used and reported in NSRDB? So to start, we have them in our publications, but I'm not sure if we have them in the website. So Grant, do you have any input on this?
Yeah, the cloud types are recorded in the datasets attribute, the units attribute for cloud type. And so you should be able to explore this in HSDS. I'm getting the impression that it's not shipped with the download wizard. But but it is part of the data, and we could probably put a copy of that up on the website. Also, if you go look through the questions, I've tried to answer all the people who have asked that with the appropriate cloud type recording. So go look through the questions, and you'll probably find it.
And yes, yeah, we can, and if we can put the cloud type directly on the website, if that's of definite interest to all our users.
I'm sorry, I was going to say they're also, if you use the API to download the data or the viewer to download the data, the cloud types are enumerated in the header of this resulting CSV file. The first couple of rows show all of the possible attributes, their units, and in some cases, such as with the cloud type, a little bit of description. So it's in the CSV, but it's like way off to the right. So it's possible that people simply haven't noticed.
Oh, thanks, Paul.
Thank you, guys. The next question is to Manojit. Any explanation on why DNI mean byte error is so high in the Northeast USA?
Okay.
15%.
Yeah, so this is it's obvious when you start comparing with ground data. If you really think of it, basically it's when we look at DNI and we average it for half an hour for a 30-minute period using a ground point on the ground. What we're doing is there are periods of clear and periods of cloudy interspersed within those 30 minutes, while our satellite data for that 30-minute is either clear or cloudy. So we've also, and there's a paper we published in, this was Solar Paces, and if what we did was we tried to identify like times of the day or hours when it was all clear. Like now more than 90% of the ground data during that period of the hour was clear, and compared it with the DNI derived from the satellite. And what we found is that they match up very close. So most of this representation is because of your point of view, is a 2 kilometer or 4 kilometer region and an instantaneous snapshot being compared to a point on the ground over a period of time, which has maybe 30% of the time was cloudy and 70% was clear. So that is what gets represented in that variability out there. But again, when you're looking for your application, I would all request our users to think of it like, okay, you have a PV plant, which is representing, say, whatever, 2 kilometer, 4 kilometer, depending on the size of your PV plant. So which one represents your point of view better? Does a pinpoint measurement on the rooftop or in the center of your field really accurately provide you a picture of what's happening in your domain? So think of it that way. And this variability, again, I just wanted to mention, it's not an error. It's just more of like what your viewing parameters are.
Okay.
Sarah?
Thank you, Manojit. The next question is to Paul Gilman. How is this data set interfaced with SAM? What kind of data sets or columns or format do we need to use to interface it with SAM?
So there are a couple things. One is if you download the weather file from the NSRDB viewer or from the API, the developer API, the files that are returned are in a CSV format that SAM can recognize. So that's one way to get data to use with SAM. And then from within the SAM user interface, we're actually making updates right now to reflect these most recent changes. So the next version of SAM that will be out in November will provide access to all of these data sets through the user interface. So that's the plan going forward.
So the other thing, just as you can see on the screen right now, is the minimum required attributes for the SAM, PV, and CSP models have been selected by default. So if you download the default without changing any variables, that will provide you all the variables to run SAM. Okay.
Thank you. The next question is to manage it. Is the data set can be available for other countries, Middle East, and also South Africa or Africa countries? So maybe explain from the satellite coverage that we have.
So technically, it's possible to cover the whole globe. Most of our work is depending on the interest of our funding agency. So like I just showed, there's Africa is covered as part of the MSG IODC, and it's available for 3 years. That because that was funded by DOE International, and we leverage their funds to cover the whole region, which is the Mediaset IODC coverage. So instead of producing one country, we produced the whole satellite data and made it available. So again, it is technically possible right now. What we do is this funding, the NSRDB, is primarily funded by the SOAR program of the U.S. Department of Energy, and the SOAR program is focused on primarily U.S. Of course, the GHOST satellite covers North and South America, so we have leveraged it to provide you data for North and South America. If we have funding agencies in the future providing us funding to go to Asia, we will make it available. But again, it's more of a funding issue than a technical issue.
Okay, thank you, Anju. The next question is to you. Well, what is the core difference between TMY and TMY POA?
Oh, okay. So yes, so the TMY is just one representation where it's only considering the horizontal orientation. So that's what a TMY is. So it's a median of multiple years. So if it's January, a median of all the Januaries within our data set, Februaries and whatnot, and that shows up in the TMY, but it's only for a horizontal orientation. So what we found is that that's okay if you put your PV panels in horizontal. We never do. So if you were to put your PV panel at a 30 degrees or latitude tilt, let's assume that, then what we would need to do is first convert our GHI to POA, and we create the time series for all the years, and then build a TMY, use the same method, but then create the TMY using that POA time series. So then you will get a more accurate representation of the TMY for that particular orientation. So that's the difference. And we've noticed, and Aaron, I think you published this paper in PVSC. So please have a look at that paper, which shows the impact of using a POA TMY, where you consider the full time series and generate a POA, generate a TMY for that POA versus just converting the TMY in the horizontal to a POA. There's significant differences there.
Thank you, Anju. And the next question is to you too. Is site adaptation implemented in the dataset?
No, there is no site adaptation implemented in our dataset. Our dataset is strictly what we derive from our satellite and our ancillary data. We do not implement any bias correction or any other direct statistical correction to any of our data sets. So we leave it in the format of what the satellite does. No ground data based correction was ever implemented in any of our data.
Okay. Are the plans to make available the TMY3 class 1 datasets from 1961 to 2005? I think I can answer this one. As Manojit said earlier, the TMY3, TMY2 datasets are archived, and we don't have any plan to use the older model, which is a statistical model, to develop this dataset, because we have this physics-based datasets on a 2 kilometer by 2 kilometer or 4 kilometer by 4 kilometer And the TMY dataset is developed using the 4 kilometer by 4 kilometer. So we recommend users to use this gridded TMY dataset instead of the TMY3 and TMY2 datasets. Manojit, do you want to add something on this?
Yes, and I can see we've had, anecdotally I can mention, is that there have been people who have occasionally used the older TMYs and have come back to us asking us, why is this so different from what we are seeing on the ground? And then we have pointed them to our gridded TMY, and I've had feedback that, well, this looks much better. So I would request, even if it means a little bit of change in your algorithms, please put in the effort to change your code to be able to take this new TMY. And I can guarantee you it's definitely more accurate than any of the older TMYs.
I think we covered most of the questions, and we're going to answer some of the remaining questions, and we'll post all the questions and answers in our website. And thank you, everybody. And maybe Paul or Manojit.
Yes, so thank you, everyone. And I think we had a full house. And at some point, I think we might have reached our limit of 500 attendees. So I'm just apologizing to everyone who couldn't get in. But we will send out an email to everyone and point them to our presentation, and you can look at it. And of course, if you have any questions, please contact us, Aaron, at nsrdb@nrel.gov. That's our email address. That will, if you send an email to nsrdb@nrel.gov, it reaches a few of our team members, and we'll try to answer the questions best we can. And finally, I really appreciate the support we get from our users. Ultimately, because this is a US DOE funded effort, DOE definitely looks at relevance, and our users make this data set relevant, and DOE continuously, we report our statistics every quarter to DOE for our users. So if you have an additional feedback, and if you think this data set has helped you in any way in your work, an occasional little note from you would go a long way in keeping this effort going, and getting support from the higher levels of DOE. So if possible, take a little bit of time. And again, I'm just a request to all our users, if you see a benefit, please send us a short email, which we can then send to DOE as evidence of the usefulness of this data. Again, thank you for taking the valuable time to attend our webinar. I think we're at pretty much close to the end of the time. Paul Gilman, if there's anything else to add on, but we're going to close it at this point. Thank you, everyone, again.
Thank you, guys.
Thanks.